Many of you'll know I'm a professor at the University of Bath, but I'm a newcomer to amateur radio. I've been a radio scientist for all of my career, but I only came across the amateur radio community in 2015, and I felt really challenged to understand radio from a different perspective. I took the amateur radio course and I obtained my call sign in 2016. My talk will start with an introduction to the space weather environment, and then we'll go into some connections between radio and space science. I'll talk about some recent work where amateur radio and citizen science are adding great value to the observational data that we have and to the scientific community. I'll also talk about how people can get involved. I've had the privilege to work with some really interesting and inspiring students over the years, and I've caught up with some of them recently to get their perspectives to share with you. The people we'll hear from later on are Zama Katamzi Joseph, Talini Pinto Jayawardena and Chris Deacon. Zama is a research scientist at the South African National Space Agency. She researches into the Earth's ionised upper atmosphere and is interested in dynamical behaviour. Talini is interested in the engineering aspects of space and radio. She built a space weather payload for a small CubeSat and has applied her engineering skills with navigation company Spirent Communications. And we'll also hear from Chris Deacon, who's an inspiration to many of us with his 6-metre work and his deep knowledge of sporadic E-propagation. All of them have different stories about how they came to radio or space science, but the commonality that shines through is their enthusiasm, as we'll see later on. But first, let's turn to thinking about space. This picture shows the Earth in space, and it depicts the emptiness in the 93 million miles between the Sun and the Earth. But in reality, there's much going on, with all sorts of interesting physics in that void. There are electromagnetic waves, light, yes, but shorter and longer wavelengths outside of the visible range too. Sometimes we have radio waves of varying frequencies that emit their energy in more intense and variable forms. They're called solar radio bursts. There's ionisation in the form of charged particles, atoms and molecules that stream out in the interplanetary magnetic field. This visualisation from the New Horizons mission to Pluto, created by NASA's Scientific Visualisation Studio, presents a slice of the data through the ecliptic plane, the plane in which the satellites of our solar system orbit. Remember, Pluto's a bit above this plane, so they've projected it down into the ecliptic plane for the picture we're seeing. 3 different variables are presented in this model: temperature, density and pressure gradient, all simultaneously but using the red, green and blue colour channels of the colour image. I love this visualisation. It reminds me of the starting titles to the Alfred Hitchcock film Vertigo. But what I find useful about the animation is the visualisation provides a depiction of the outflow of the spinning sun, a bit like the outflow of spinning water from a water sprinkler. This is helpful because it explains part of the complexity that we have in the prediction of a big solar storm hitting the Earth. This next NASA animation shows a large solar storm event with coronal mass ejection of particles streaming through space and bombarding the Earth's magnetic field that shields us from a radiation storm. As the interplanetary magnetic field streaming out from the Sun encounters the Earth's magnetosphere erodes on the day side and reconnects on the night side in a cycle that drives the magnetospheric convection and disrupts our polar regions. You can see in the animation the polar outflow of neutral atoms into the magnetotail and the precipitation of particles causing the aurora. The diagram is also useful to show more of the overall picture at the same time as we watch the movie. Now, most of the amateur radio community will be very familiar with space weather because it affects our HF propagation. For example, the solar cycle effects on propagation It changes the bands that are supported for our HF communication. And this brings us to the all-important topic of the ionosphere, the bit of space weather that I'm most interested in. The ionosphere is the ionised region of our upper atmosphere. It's where our atmosphere meets space at about 80 kilometres altitude and extends upwards to many hundreds of kilometres. It's the region of our atmosphere that lights up when we have the aurora. Right at the lower edge of the ionosphere is a very interesting region that you can sometimes see in the late twilight in the form of noctilucent clouds. These ice crystal clouds are up at similar heights to the ionospheric E layer. There's more coming on about the sporadic E layer later on in this talk. But for now, the important point is that there are traces of waves in the photograph that are indeed indicative of real atmospheric waves that drive into the lower part of the ionosphere, and they make it very dynamic and variable, and they affect our communications. It's a very interesting region to study. But next, we'll turn away from optical observations and back to radio. Ever since Sputnik in 1957, we've had satellite radio signals available to collect on the ground. It's estimated that there are now over 3,000 satellites in orbit, and we know that there are planned to be a very large increase with the financial cost of the access to space rapidly coming down. Most of these satellites are using radio links to communicate back to Earth, and in particular, the navigation satellites provide excellent signals to sense the ionosphere. The diagram here shows the sort of coverage you can get with the radio signal shown in yellow and one of the radio signals from satellite to receiver highlighted in magenta pink. We'll look at that one in more detail now. Each radio link makes a separate satellite to ground path, and the measurement itself is the delay of the signal propagation as it passes through the ionised region. Effectively, the more ionisation, the slower the signal travels. So if you can measure the time delay from when the satellite signal set off to when it arrives, you can work out the excess path time over and above what it would have been if the same signal had travelled through a vacuum. However, this is not quite so straightforward because the timing synchronization you would need is very difficult to achieve between the satellite and the receiver. So there's another better way. If you have two radio frequencies, the lower frequency travels slower than the higher frequency. This is dispersion. And you can use this property to work out the total ionisation along the path. The wonderful thing about this is that it allows for cancellation of a lot of the error terms. Now this brings me to how I entered this field of research. As a physics undergraduate in Aberystwyth, I was interested in mathematical puzzles, and the topic of medical imaging was one such type of problem. Aberystwyth was pioneering a new idea that had been proposed by KCA in America to apply medical imaging methods to UHF-VHF transit satellite radio signals to image the Earth's ionosphere. And I was lucky enough to win a PhD place to pursue that research, and hence I started my career in the new field of ionospheric research and experimental radio tomography. After I moved to Bath, it was becoming clear that the future of radio tomography was moving into ionospheric data assimilation, and that we could use the new GPS signals. This picture shows us the sort of information that this can provide using GPS radio observations to image the 3D ionospheric electron density in the space weather Halloween storm of 2003. So that's my entry into radio science. Now we'll meet some others who came along different paths. I'm delighted to introduce to you Dr. Zama Katanzi Joseph. I first met Zama at a space weather school in South Africa. She came to Bath to pursue her PhD and then returned as a radio scientist to the South African National Space Agency. I asked Zama to share with us how she decided to study space science.
I was actually exposed to the field when I was a teenager in high school, and I watched the movies Armageddon and Deep Impact.
Okay.
And astrophysics was so cool, and it was vastly different from any of the careers that I was exposed to in high school, like medicine, engineering, and accounting. So that appealed to me, that not only was I going to do something that was exciting, but also very different to what my peers were exposed to.
That sounds really fantastic. And how did you actually get into radio science?
So I started in radio science when a new program in my country, in South Africa, was created to train the new crop of astrophysicists and space scientists. And the host of the university that hosted the program was actually the university where I did my undergraduate. And one of the courses that we were offered was radio science, and I related to it better, and it seemed more applicable to me than the astrophysics side, which I was initially interested in, so that I decided to switch.
We'll hear more from Zama later. The best-known space weather event happened in 1859 and was documented by the astronomer Richard Carrington, who made the connection between sunspots, the aurora, and the magnetic field events on the Earth, with what has become known as the Carrington event. This was the largest solar storm in modern history, although we now know that the Sun still puts out events of this magnitude because there's been several large events since that one. One in particular narrowly missed the Earth in 2012, as it was recorded on one of the stereo spacecraft. But back to 1859, from the New York Times on September the 3rd, 1859, there was another display of the aurora last night, so brilliant that at about 1 o'clock ordinary print could be read by the light. The effect continued throughout this forenoon, considerably affecting the working of the telegraph lines. The auroral currents from east to west were so regular that operators on the eastern lines were able to hold communication and transmit messages over the line between this city and Portland, the usual batteries being disconnected from the wire. The same effects were experienced upon the Cape Cod and other lines. Of course, there are important applications to space weather where it affects our technology today. We can see weather by looking out of the window, but it could look like a beautiful calm day, and yet a space weather storm could be raging overhead. So we need other ways to monitor and predict space weather, because it does have important effects on our modern technology. The major effects are on the power grid, where transformers can be overloaded and burn out, and where communication systems are disrupted. Radio amateurs know very well about radio blackout from solar storm events. But a recent paper highlights the complex vulnerability of our modern technology, where intercontinental optical fibre communication links have a vulnerability because of their electrical cabled power lines and repeaters. If these were taken out by a large storm, the loss of the major internet services would be at a severe risk, and it could last for considerable periods of time. This is of interest and discussion in the community at the moment. My main area of interest has been on the effect to navigation services, such as GPS, Galileo and GLONASS, which are affected in multiple ways. Solar radio bursts were first found to affect GPS by Cornell University researchers in 2006. The effect is similar to radio jamming, but this is direct radio interference from the sun, and it affects the part of the Earth that's facing the sun. And it can result in a satnav having a temporary loss of service. Another important ionospheric effect is radio scintillation. This is the breakup of radio signals by diffraction and refraction, and it can result in both rapid amplitude and phase changes to the signals. Understanding these effects on navigation signals is really important. I caught up with expert Dr. Talini Pinto-Jayawadena. She has applied her knowledge of radio engineering and electronics to the navigation industry, working at Spirent Communications on an Innovate UK knowledge transfer partnership. I asked her how she entered this field, and I asked her how training as a radio amateur has helped her.
I think from the very beginning it was the unknown and the mystery surrounding it. But I think I really got into space science when I first spotted Jupiter through binoculars during a school project. And I was amazed that I could actually see another planet through my own eyes. Radio amateur course is very much focused on the RF communication side of engineering, and you can do it at your own pace as well. An engineering degree would cover a broader range of topics, and it would span for 3 to 4 years. So this is very much a focused area in communications.
And what was specifically really useful about the radio amateur course?
What I found useful was that the course is very practical. So it helps you understand how a radio works, how to build or set up your own radio, and also how the different external elements like the ionosphere can affect a communication link. So it was this hands-on practical experience, and applying it directly from what you learn into practice is what I really found useful.
I also asked Spirent about the industry need for people with radio skills and how they can get started. And they said, we need more people like Talini with a real interest in radio and with practical skills. We offer a range of different early career opportunities at Spirent, from work placements and ways to gain industry experience, exciting career opportunities like internships, apprenticeships, and graduate opportunities. At Spirent, there's an opportunity for everyone. Now, most people are going from a start as a radio amateur into a radio science career, not the other way around like me. So I asked Chris Deacon about his journey into amateur radio.
There was just that fun in sort of making something work, and that sort of appealed to me. Just sort of press a button and the light comes on or whatever it is. But one of the kits there, one of the circuits that you could make was a medium wave radio, and I remember doing that and playing it. I mean, I think the small kit you had to plug an earpiece in, and the larger kit you had a speaker, and so that sort of. I mean, the interesting thing is that at school, I was more interested in chemistry when I was sort of in my early teens, but gradually over time became more into physics. And I think amateur radio had some part to play in that. But then the sort of the community side of amateur radio comes into it. I had a couple of friends who were in my class at school. I'm thinking now about 15 years old, something like that, 14, 15, 16. And they sort of brought me along to the local radio club. And also there were a couple of local radio amateurs who lent me a receiver, an old military thing. And that got me listening on the radio. So I had the sort of classic shortwave listener introduction to amateur radio. And I got my first license, which was a Class B license, the G8 license, no Morse code in those days, when I was 16. I well remember my first contact. My friend lived in a tower block. I was up near the top of this tower block using his radio, and that was my first contact on 2 meters. I remember very well.
Many of you will know Chris. Chris talked about his entry into amateur radio, but recently he's taken the step into applying his lifelong experience of radio to study details of sporadic E-propagation using the 6 meter band. He's interested to find out whether the reflection mechanism is specular, like a reflection from a mirror, or magneto-ionic, where the signal is continuously being refracted by the ionosphere.
I became interested in how the signal gets from one place to another. That's the most interesting thing about radio to me. Obviously, other people are different. And the sort of miracle almost of a sporadic E signal that it just appears out of nowhere. Now, one of the things that I wondered about was, well, actually, sporadic E signals are well known for varying up and down like crazy. They can appear out of nowhere, they can disappear within minutes. And I came across a little bit of perhaps not thoroughly sort of rigorous research, but some various people talking about the effect of polarization on the signals that we receive. So that if the polarization is aligned with our antenna, we get a strong signal. If it's at right angles, we don't.
Thanks, Chris. We now turn to look at another project where radio science is getting help from the amateur radio community. Sam Lowe was starting his PhD at the time that my research group were becoming connected to the amateur radio community. Sam was one of the students who started the amateur radio course with me. In America, the amateur radio groups work with the radio scientists in a group called HAMSci, which is led by Nathaniel Frizzle. This connection to HAMSci brought us a really interesting project for Sam's research. Sam's project is fascinating. It builds on the revolutionary advances through software radio and the internet, where it's now possible to record millions of radio links every hour across global networks. One of these networks, the Weak Signal Propagation Network, WSPR, was used by Sam. Sam looked at some of the frequencies that are commonly propagating between the United Kingdom and New Zealand. The question that Sam was interested in was to see how we could use WSPR data for science and what it could tell us about propagation over long distances. In particular, we wanted to test the hypothesis that signals would be clustered around the terminator times. Sam and I worked alongside with Ben Whitfleet to investigate this grey line propagation phenomena. The figure shows the time of year on the horizontal axis and the time of day on the vertical axis. If you look at the solid shading, the pink colour is the UK daytime and the blue is the New Zealand daytime. The yellow is common daytime and the white is common nighttime. You can see when you look at the figure that the number of radio links from the UK to New Zealand are overplotted on the background. The results clearly show a terminator grey line clustering. This is all very good and it's what we hope to see. However, the really surprising result that Sam found was that the propagation in the opposite direction is not symmetric. So the New Zealand signals are received in the UK morning at sunrise, but they're not received in the UK evening at sunset. And we're not really sure why this is. This all led on to more questions, as research often does. What we were able to find out was to confirm that the grey line times do indeed exist, so there's a clustering around sunrise and sunset. But of course we don't know the full propagation path of the signal. What we know is the transmission point and the reception point. In the future, we want to investigate the full effects of the diurnal HF noise variation at either ends of the path. The PhD student who did this research, Sam Lowe, said, "My project started through HAMSci UK, an NERC-sponsored event to bring radio scientists and radio amateurs together. It's been very easy to access the WSPR data, which was collected at over many years at multiple locations and multiple frequencies. This has been a tremendously useful resource for my research, and I want to say thank you to everybody who's contributed to it." I want to end now with a big warm welcome to the community and a warm invitation to everybody to get involved. I hand over to Zama for her words first.
My advice would be to actually talk to as wide a community as possible, because space science is very diverse, not only in the topics that people actually research into, but also in its nature. So you have more theoretical people who maybe like thinking things in abstract or philosophical, and you had other people who are more analyzing data and, trying to find, explanation for what they're seeing in the data, and more maybe hands-on people, more engineering type people who are more instrumental. So if you talk to a diverse people, then you get to actually find out what each area of space science or radio science is all about, and you get more information so you can make a more informed decision. And I want to say to especially young people that usually when you think about a scientist, you think about a person who is more narrow-minded and only focused on their work. But actually scientists are very friendly, and they like nothing better than, convincing another young mind to join the field. So talking to them will be actually not only advantageous to the young person, but also to the scientist.
I've personally found amateur radio to have a tremendous resource of technology, of knowledge, and of open and friendly discussion. I'd specifically like to mention Steve Hartley, who was my teacher on the amateur radio course. But there are many others to whom I'm very grateful for their generosity, their encouragement, and their kindness. Amateur radio offers an introduction to a huge range of careers that are underpinned by radio technology and communications. Whatever is your interest or your ambition, from radio tracking of migrating birds to next generation spacecraft communications, or even listening for extraterrestrial signals using radio telescopes. There's something for everyone in radio, and opportunities for everyone to get interested in and inspired by it. I encourage you to join the community of radio amateurs. Now is the time, it's never too late and it's never too early. Get involved by collecting radio signals for WSPR, or go and get some work experience at a local company, and maybe they'll sponsor your degree, or apply to university or for an apprenticeship. My career has taken me literally to the ends of the earth. This is me at the South Pole Station in Antarctica on fieldwork in 2010. What a huge privilege and what a job it is. There's a lot of fun, hard work and satisfaction working in radio science. And as Zama said, it really does offer a range of opportunities. There's something for everyone, so please do get in touch. Combining a US amateur radio extra class license with a PhD from Stanford University in electrical engineering has permitted access to the world's most powerful HF transmitters, ISCAT in Norway, HARP in Alaska, and Arecibo in Puerto Rico. That's from Paul Bernhardt. For me, one of the highlights of my radio career was operating a high-power UHF space weather radar in northern Scandinavia. With a transmitter with a 1.2 megawatt klystron, an 80 kilovolt power supply. Big stuff. I even learned that you can move the 32 metre dish antenna by hand when the drive motor broke. That's Bob Meggs. I was participating to an examination for gaining a permanent position at INGV, and they suggested to be prepared on the ionosonde. At that time, I thought to be a balloon sonde, similar to those used for atmospheric sounding. I enjoyed and still enjoy to work on polar sciences in the frame of Sun-Earth interactions and space weather, and I participated to several expeditions in Antarctica and the Arctic. My favourite part of space science is collecting and seeing new data on the ionosphere. That's from Alex Chartier. And for the past few years, I've been working with images of Saturn's auroras captured by the Hubble Space Telescope and Cassini missions. It's a privilege getting to see something so very far away and so different from home in such intimate detail, and I never take it for granted. And that's Jo Kinraid from Lancaster University, and both Jo and Alex went to the South Pole Station in Antarctica. And Jo adds, "No call sign sadly, but I really want one now." And Larry Paxton from Johns Hopkins University. "The thing I most enjoy about my job is the excitement, intellectual stimulation and fulfillment that comes from working with a diverse community to solve a challenging problem." Chris Budd, mathematician from the University of Bath. "I've worked in radio all of my career since starting at Marconi in 1979, and I was a radio amateur before then, and I'm still active in amateur radio. I love the technical challenges that it poses and the way that I've been able to solve many of them using mathematics." Gemma Attrill from DSTL. "I really enjoy working at the interface where science meets engineering. I'm continually learning." Phil Erickson from MIT Haystack in America. "Radio science allows me to collaborate across the world on discovery investigations for issues that could not be more important to society. Space weather, communications, and other environmental issues." Lucilla Alfonsi. "What I like more is the interaction with students and early career scientists when they discover how multidisciplinary is our job, especially for space weather applications." Mike Hapgood at Rutherford Appleton Laboratory. "Working with so many people across the world and at all working levels, from the simplest jobs to some of the most distinguished people in our field, it's shown me the importance of diversity and of understanding other people's needs." Pierre Cilia from South Africa. "Undoubtedly, what I enjoy most about my job in space science is the excellent collaboration and sharing of expertise and resources across space scientists, which has proven to be a great stepping stone in my career in this field. And with it, the opportunities it provided me to travel to conferences and to meet like-minded colleagues and to work with them." Chris Scott from Reading says, "If I had to choose one thing, working with amazing people from all around the world." And Nathaniel Frizzle from Scranton in America. "The thing I enjoy most is meeting and working with the many different fascinating people in the radio science and the amateur radio community. I think it's a great community to work with." And many of you will know Nathaniel as the HAMSci lead. And a radio astronomer, Carol Mundell. "I love that, as a radio astronomer, I collaborate with brilliant radio scientists and engineers around the globe, transcending national boundaries and making lasting friendships, whatever the political climate of the day." And we end up with Paul Cannon from the University of Birmingham. "The excitement of discovery, making a difference, teamwork, travel, and perhaps above all, friendship."
Well, Cathryn joins us live now. Cathryn, welcome to the RSGB Online Convention 2021. And you'll have to imagine the huge round of applause you normally get at this point, I'm afraid. I've got some questions for you, but I'd like to start with one that's a bit personal. I mean, you've had your amateur license for a few years now. I think you said 2016. Away from your space research, do you actually ever go on and have a chat on 80 meters or chase awards or go in contests?
That's a brilliant question, Jim, and I was expecting that somebody might ask me that. I have to say that I don't go and chat on the radio, and I'll tell you that I think this is a really good example of how it has something to offer for everybody. I'm quite let's say quite a private person in some ways. I get a huge amount of input from intellectual stimulation, from reading, from technology, from playing with technology, from interacting with people as well. But my real driving interest in radio is really the technology side. And I think that one of the things I've massively benefited from in working with the amateur radio community is to actually understand the personal experience of people. And I'll give you a specific example of that. So we heard from Chris Deacon, and Chris is pursuing a PhD at the moment. Chris and I obviously have got to know each other through his sporadic E work. And one of the things that's happened is that with Sam's work, when we were looking at those radio signals and looking at the times that those signals arrived, obviously, big database like WSPR can tell us the answer to when that happens. But actually, just a quick word with Chris was able to tell me, yeah, they come through in the morning from New Zealand, just 2 minutes. The knowledge and the expertise in the community is absolutely phenomenal. And I massively respect that. But yes, I have, let me just say, I've got a few amateur radio friends who are determined that they're going to get me on the air. So I think it is going to happen. In particular, I can tell you that Bob Meggs, who you heard a quote from earlier, Bob Meggs, I think, has some ambition to get me chatting, and I think it will happen. Definitely.
Are you and Talini and Sam, are you rare in the scientific community to realise the value of amateur radio, do you think?
I think that it's something that had quite a divide about 10, 15, 20 years ago. So when I entered this field for my PhD, I didn't really know anything about amateur radio. Weirdly, one of the strangest things is that my father and my uncle were actually part of the radio listeners during World War II, the voluntary interceptors. And when I started my PhD, my uncle said to me, "Oh, you're going to study the heaviside layer." And I had no idea that it was called the heaviside layer. So there was this historical family connection to radio, which was very bizarre, that I ended up, because of my interest in mathematics and puzzles, I ended up in a field doing something actually very similar to what they did as volunteers when they were younger. But I think that generally, in terms of where things are now, it's really all changed with the HAMSCI work in America that's led by Nathaniel Frizzle, because what they've done over there and what we've really adapted here to start to do as well is to understand how valuable the amateur radio community resource is. And also, it's not just about collecting the signals and using the data. The depth and breadth of knowledge amongst the community is phenomenal, because it's not just, there is practical experience, there's amazing practical experience, but there's also, I think, deep technical knowledge, because a lot of radio amateurs, of course, actually are professional radio scientists as well. So, for example, my colleague at Leicester University, Mike Warrington, many of you will know him as a radio amateur, also a professor of radio science. So I think it's increasing amongst the younger people now, that they start to realise the value. One of my students, Heba Elsaleh, she said to me that when she was doing her PhD, that it was very theoretical, but actually when she started to do the amateur radio course, what she was able to do is to gain that practical confidence, and it really fed back and gave her confidence in her work. So I think it's increasing.
You might be interested. We've got to talk about the Radio Security Service coming later in the day on the.
I'm looking forward to it very, very much. I really am. We have, yes, yeah, very
Ian,
much.
In Durham, 2E0INX, he said you mentioned the course for amateur radio. More details. You mentioned Steve Hartley helped you through that.
That's right. So I was really fortunate. By chance, Steve Hartley, who runs the course in Bath, obviously I'm in Bath as well, so I was lucky geographically to be in the right place to be doing the course. I can tell people a little bit about the course from my experience. So there's three different stages. There's the foundation, the intermediate, and the full license stage. And the foundation course is really quite accessible, I would say, to everybody, in the sense that you don't require a lot of technical knowledge to start the course. You just need to be interested. That's all, just to be interested. It was about 10 weeks. It was very stressful for me. It was very funny because there's me, professor, leading this research group in radio science. And of course, my PhD students decided they would come on the course as well. And the pressure on me to actually perform into the exam was quite high. It was quite funny. It was all very friendly. But there was an expectation that if I was not to pass this exam, that I would never live it down. So that was the first part. The intermediate part then started with some practical work. So we did some radio build, some soldering to build some I think it was a 7 megahertz signal that we were picking up. So we built a simple kit. And then we started to really accelerate into some of the more of the technical knowledge about amateur radio. And then the final part was really very advanced. I have to say, it's very advanced. It was very, very, very interesting. And I don't mean advanced in terms of too difficult. I just mean there's a lot of material, really fascinating, really interesting. And for me, personally, as a radio scientist, it was really interesting to see my own subject taught from a different way. And I learned so much about teaching from listening to Steve teach us about, because the ways that you can explain things, the ways that you can understand them, and also to understand the interplay between the theory and the practice to happen very quickly with amateur radio. So if you're studying a subject in school or at university or technical college, you normally would have, even maybe an entire module or entire course, which would be quite theoretical. But with amateur radio, it's back and forth all the time. It's all about, does that really happen? Practical experience. And of course, the training that gives you, if you do this before you become a scientist or an engineer, the training that gives you in the feel for real world systems is phenomenal. That's an expertise that's really uniquely found within this community. So I would thoroughly recommend it to people.
I had a message from Rachel Sanders who said, Cathryn, I was a physicist long before I was a radio amateur too, and I'm not into operating. That's fair enough. Now, Murray Nyman has given me a cue to what I thought might be a bit of a daft question to ask you. Murray says, please do transmit and warm up the ionosphere. And I was going to try and ask you a question about this. We know about the external influences on the ionosphere from the sun, etc. What about from this side? Because I had a friend who said to me during the current previous doldrums on the bands, the ionosphere is not doing very much because all the high power shortwave stations are closed down, and then nobody's heating the ionosphere anymore. Is there anything in that?
Yeah, this is, and now let me just start by saying, this is something that I started entering this community, and I always start because I'm really an experimentalist. And I always start on the basis that if people tell me something, it's probably true. Okay, that's where I start from. So I start from that, and then I think, okay, let's look into it in more detail. I don't start from dismissing things, because as a scientist, you look for the evidence. So in terms of what are the effects of the HF signals on the ionosphere, well, we look at the ionospheric heaters. So one of the people I spoke to in preparation for this talk was Paul Bernhardt in America, and he works a lot on the HARP facility up in Alaska. And the HARP facility is a big, high-powered radio facility, effectively called an ionospheric heater. And so the term heating, what it does is it pumps RF energy up into the ionosphere, and then you can create irregularities in the ionosphere. So you're actually modifying it using this ionospheric heater. There's another facility up in Tromsø in Norway, does a similar type of thing. So yeah, absolutely true that the radio signals that you send out will have an effect in the ionosphere. Now, the question then is, I guess, how many radio amateurs would need to be on air at one time to actually have a measurable effect? There's a great scientific question. And how closely do they have to be packed together? Can you citizen science create something like like HARP? I don't know. Really, really interesting questions. And that's the sort of thing that, so when you say, you started off by saying, I'm not sure if this question is really, sensible, you start to explore the question and you lead to a really, really interesting scientific question. And then you can start to think, well, how could we measure that? What could we do? It's incredibly difficult with the ionosphere because the ionosphere is such a live beast. It's always doing something. So it's affected by the waves coming from below. It's affected by the space weather from the sun. So actually teasing out the effect that would be coming from the radio amateur signals would be a big challenge. But we like challenges. Maybe we should all get together and organise a day or something. And then send you all our information. Cathryn, our time is up. I'm very, very sorry, but thank you so much for taking the time to give us that fascinating insight into the links between radio and space research. We really do appreciate it. And so you're welcome to stay and watch the proceedings. But if you've got research to be done, of course, all the streams will be available later in the day. But thank you for now. Thank you so much. Thank you.